right, so to place this talk in this whole conference, think a little bit about what was the first keynote talk yesterday. Do you remember the topic of the first keynote? Sustainable AI, right? So to place, so one of the takeaways from this talk yesterday was that actually the small use case specific models are more sustainable and are actually a way to go for many applications. And in this talk, I will give you some example of how to create such application-specific systems using domain knowledge and our favorite loss functions, because there have been many loss functions in this session and also yesterday. To illustrate how to work with this kind of approach, I introduced you to a use case that we worked on, and this use case is gas turbines. Why are gas turbines important to energy transformation? Gas turbines are a backup to renewable energies. So whenever you have, for example, not enough of solar or wind, gas turbines come for help. They are quick to start. They can work when there is no enough renewable energies. And also, they can even work with different types of fuels. So they can even work with hydrogen and be carbon-free, emission carbon-free. And it is important when we model energy systems, especially energy grids, to be able to model such energy systems like gas turbines, so that we can simulate their and find the optimal use for them in the electrical grid. So let's take a look at a task of dynamics, temporal dynamics modeling, which treats a gas turbine as a black box. So I would like to address the right part of our audience. So we see here on the top the input of such a gas turbine, and on the bottom we see the output. Can some of you tell me what are the two differences between the input and the output of this gas turbine? What is the kind of things that comes up to you? Apart from colors. The ramps, yes, the ramps is one thing. So you see there is a delay. So there's a delay that is caused by the operating of the gas turbine. And there is a different issue here. Take a look at the y-axis. Noisy. Take about the levels, the values. The input levels are different than the output levels. Okay, so basically our task here is to use a machine learning to actually learn this kind of behavior, the black box input-output behavior. How could we approach this problem without machine learning as an alternative? This is theoretical modeling with the help of the so-called Rowan model, so which is a model that is based on equations, actually almost 50 years old, and it is commonly used to model the complex mechanics of gas turbines. The problem is it doesn't work for black box approach. If you only have input and output problem, it does not work. You need to measure every single smallest part of the gas turbine. So this will not work in our scenario. So as an alternative, of course, we can try to use simple data models. For example, here on the bottom right, you see like a simple curve fitting that was explored by one of our co-authors during his PhD topic. But this approach also has a problem that it is mostly like a rule-based approach. It's hard-coded, and as you see, it's not really perfect at these ramps that we actually care about in our model. So let's see how can we now apply machine learning LSTM networks. Let's see what happens. Now I will address the last part of our audience. So what we see here is just the output. So we are not considering the input of the gas turbines, only the output. Can some of you tell me what's the problem here between the generated prediction of our machine learning model and the ground truth that we were expecting? What is the problem here? They don't match, but where exactly do they don't match? Yes, so the ramp is not present exactly because basically it was not present in the input signal. So our machine learning model learned input signal by heart, and because of this, like there was no incentive for the machine learning model to learn the ramp, so it didn't. And this can happen especially if the training data is small. And this is exactly where we can use knowledge-guided machine learning, where we actually use any kind of knowledge about the problem to just help the machine learning model do the useful thing. And in this case, it would be exactly the same answer as I got from the right and the left, which is ramp and different signal levels. So we try, and now the question is, so how do we approach this problem? So we observed that our problem has these ramps, and these ramps, they actually are constant. They are constant, but they are, of course, constant only with respect to specific time frame. So basically, we observed that this our prior knowledge, which is actually not that formal, not that physical, like we saw with physics-guided graph neural networks, because there it was physical knowledge. This is more like observational knowledge. We observe that our output can basically have three types of ramps. Can have a rising ramp, a constant one, and the falling ramp. And now the question is, can we somehow use this simple observation to help train a useful and precise model? We decided to name this kind of observational domain knowledge as permissible system states. So these, if I go back, again, at the bottom you see three alternative states that the model is allowed to take. But the model should still decide by itself which is the most suitable for that particular moment. And the goal is now, let's guide our method to use one of those three states. We use loss function. So basically, it's a sum of two loss functions. The first element on the left is a typical loss function where we try to minimize the error between the prediction and the ground truth of our output signal of our gas turbine. And then we add additional knowledge-guided loss function, which is basically a multi-state constraint. So what is important here is just this minimum. So if you see it's there is a minimum. If you, for example, use TensorFlow or PyTorch, a minimum function is in fact differentiable. So you can use it as a selector of alternatives. So basically you can define your permissible states, penalize their deviation from your actual model state, and then just let the minimum function select the closest alternative to the one that you actually need. So minimum, using minimum as a selector, this is basically the main innovation of this paper, which is very simple, but it actually works. And I want to show you how it works. So let's take a look at this particular problem. So remember, the problem was the ramp was not there, and we actually needed the ramp to be there. So if we look, our model has had a ramp of slope 100. So it was way too steep than we actually needed it. We actually needed it to be either 6 or 0 or -6. So basically rising, constant, or negative. So again, we use our minimum function as a selector during the training process. We compute three distances. So the first distance will be the distance between the number 106. Then the second distance will be the distance between 100 and 0. And the third distance is the distance between 100 and -6. Which of those three distances is the smallest? (100 to 6, 100 to 0, and or 100 to -6? Which is the smallest distance of those three? So 100 - 6 is 94. Yeah, 26, right? 100 minus 0 is 100, 100 minus 6 is 106. So basically we have, so our method will select the state S1, which is ramp of the slope 6, right? I mean, and it will work for any kind of situation. So basically we are just guiding it to the closest permissible state, and we just hope that the closest will be the right one. But let's see if it empirically works, okay? Because maybe I mean, I cannot prove that this works. We just have to empirically say that see that it works. For that, we actually collected real data from this gas turbine that you saw at the beginning of the talk. And because collecting this data is actually pretty costly, it takes like many hours and there's a lot of personal effort. So we only create a very small data set, which is also good because in practice, when you have those small gas turbines, you don't have that much data. So it was actually reasonable and realistic. And we used 6 of them to train and 2 to test. And the results were that the top curve was the baseline. So basically the machine learning model without knowledge injection, and the bottom one is our method. And on the x-axis, you basically see what happens when we increase the number of data. And so what we see here is first, we are lower in terms of RMC by up to 40%, which is good. But also you see that basically with our approach, with just 2 data sets, so the orange curve, to train sample 2, we are still better than the original knowledge uninformed network with the entire data set. So basically, if you go back again to this keynote talk from yesterday, you basically see that you can use knowledge to create a specialized model that will require much less data. It will converge faster. So it will be also more sustainable and will be still useful and also physically, I mean, useful for the purpose. So now, these are only numbers, but let's maybe actually see the qualitative, like, let's see so the question now, does the model actually learn the ramp? What do you think? Did it learn the ramp or not? Or maybe it's just, I just faked it. So these are the results. So on the top we see the original model I showed you in the beginning. So this was what happened when we only used very small training size of 2 training samples. And this is how it worked on the tested set. And on the bottom is exact same model, nothing changed. The only thing changed is the loss function, right? So you see, you can use the loss function to basically help the network learn the thing that you want the network to learn. But still, the other aspects of the modeling, which is the levels between the input and output, this is learned from data. So we are using both directions. Your knowledge plus the data equals model. And this is exactly knowledge guided machine learning. There's also one aspect of injecting knowledge that is pretty novel, and also it's more personal to me because it's a part of my PhD topic. It's the aspect of incorrect domain knowledge. Because I mean, of course, I showed you that it works, but what if the provided domain knowledge was wrong? So what would happen then? And the answer is, it's important whenever you apply your knowledge guided machine learning, whatever kind of projects you do, it's important to perform a sensitivity analysis of your provided domain knowledge, just to make sure that first, you actually got the right domain knowledge. And second, to make sure that your approach is robust against small variations, because maybe, as we see here, if the domain knowledge that we provide to the model is very different from the actual knowledge, we actually can get worse results than the baseline method without any knowledge. So this is just important lesson learned for anyone interested in knowledge guided machine learning. So after you prepare your after you develop your method and evaluate it, also play around with changing the domain knowledge to see how it reacts to wrong domain knowledge. And then you will at least see how robust it is and whether you actually got it right. A side effect of this is also that you can basically, in theory, if you wanted to perform many experiments, which is not recommended because it's not sustainable, but you could basically just randomly train different types of domain knowledge values to find the perfect one. But of course, this is not what we want because this would increase computation, but it is technically possible. So to basically not know the exact value and just try it out by parameter tuning. But again, not recommended. So to sum up, this talk was about how to use knowledge-guided machine learning to model different dynamical systems. In this case, it was a gas turbine for the purpose of simulation, especially black box simulation. And I told you what are permissible system states. In our case, these were those ramps. But it can be anything. Actually, this was just an example how it can work in this scenario, but it's the permissible system state, it's all about, remember, this minimum acting as a selector. And anything else, your states can be anything. The problem can be also much harder than those relatively simple time series problem. It may be multiple dimensional problem. So the only takeaway I would like to for you to take is that permissible system states can be injected with the help of loss function and can help you get the same or even better results with less data and less training. Thank you very much.